In this video, we are going to build a local AI babysitter that works 7x24 with n8n and Home Assistant. This is a system that uses Frigate to listen for specific sounds like crying or yelling, and uses a local AI to visually scan for danger, giving you the proactive alerts you actually need. First, you need to enable the sound types you want to recognize in your Frigate configuration file. I've chosen to enable sounds relevant to a baby, such as crying, scream, yell, and speech. Additionally, in the camera's roles, you also need to add the audio function. Now, let's create the n8n workflow. Everything begins with our starting point, the schedule trigger. For this project, our goal is 24/7 uninterrupted active monitoring. So in the configuration, we've set the mode to every minute, and for the interval, we've chosen 5 minutes. You can of course adjust this 5-minute interval based on your system's performance and specific needs. This simple setting is the heartbeat of our operation, kicking off a complex hearing and seeing check every 5 minutes. Alright, so every 5 minutes the timer triggers our workflow. The very first thing it needs to do is listen for any abnormal sounds in the room. This is the job of the first node in our audio branch, an HTTP request node that I've renamed Crying Sound. Let's take a closer look at its configuration. First, we set the method to get. In the URL field, we use an expression to dynamically tell Home Assistant we want to query the history starting from exactly 5 minutes ago. Under Query Parameters, we add 2 filters. First, filter Entity ID to target only the Frigate crying sound sensor, and second, End Time to dynamically set the query's end time to right now. Finally, since we're calling a protected Home Assistant API, we need to authenticate. We enable Send Header, and in the header parameters, we add authorization for the name, and for the value, we enter bearer followed by your Home Assistant long-lived access token. With that set up, this node will precisely fetch every log related to crying from the past 5 minutes, ensuring we never miss a thing. Okay, now we have the sensor history, which might be a list of several on and off states, but we don't care how many times it triggered. We just need a simple yes or no answer. Did a cry happen at all? This is the core task of the code node that follows. This node acts as an efficient yes-no checker using JavaScript. It quickly scans all the history records, and as soon as it finds a single state that is on, it immediately stops and returns the number 1. If it gets through all the records without finding an on, it returns 0. Now it's time to act on that judgment. This brings us to the next node, the if node. Its purpose is to decide which path to take. In its configuration, we set a single, simple rule. Does the output from our code node equal the number 1? If the answer is true, meaning a cry was indeed detected, the workflow proceeds down the true path to start our alert process. If it's false, the workflow exits, and this audio check ends safely. So our if node has just confirmed a cry was heard. The workflow immediately flows down the true path to execute the first step of our alert, see what's happening right now. This is the job of the Call a Service node, which I've renamed Crying Sound Snapshot. It commands a specific camera to capture a snapshot of the current moment and save it in Home Assistant. In the configuration, we call the Camera Snapshot service. There are 2 key settings here: file name, where we define a clear save path and name, and entity ID, where we tell it precisely which camera to use. We've successfully saved a snapshot. Now for the final step, sending that picture along with an alert directly to us. This is the task of the last node in this branch, Send Image. This is another HTTP request node, and its purpose is to call Home Assistant's notification API to send a rich text notification with an image attachment straight to our mobile phone. In the configuration, the method is post. The URL points to the Home Assistant Notify service for our mobile device. We also use Send Header for authentication, but the most critical part is the body. Here, in JSON format, we define the notification. The message is set to Crying Sound Detected, and in the data field, we add an image field that points to the URL of the snapshot we just saved. And there you have it, the complete process for crying detection. This same powerful logic, from querying history to making a judgment to taking a snapshot and sending an alert, is duplicated for our other audio branches, like yell sound, speech sound, and scream sound. The operations are identical. We only change the sensor being monitored and the notification message. But what if a sound occurs that the AI doesn't recognize as a cry or a yell? To catch these unknown, sudden noises, we've added a sound level monitoring branch as a safety net. The logic here is a bit different. It doesn't identify the type of sound, but monitors its intensity. Its code node checks if the decibel level at any point has suddenly spiked above our threshold, for example, -50 decibels. This ensures that any sudden, abnormally loud noise triggers the same snapshot and alert process, keeping us aware of any potential danger. Now, having covered all of our audio monitoring, let's switch gears to the other equally important lifeline, our visual monitoring branch. This branch periodically uses AI's eyes to check that the scene itself is safe, even when there are no sound alerts. Its journey starts with our first node, Snapshot. Its role is critical. Every time the workflow runs, it immediately commands our camera to capture a fresh snapshot. In the configuration, we simply call the camera snapshot service and specify a fixed save path and name. Okay, a fresh snapshot is saved in Home Assistant, but here's a key technical detail. The service only saves the picture to a folder. It doesn't pass the image data into our workflow. To get the image to our AI model, we first have to download it. This is the core task of our second node, an HTTP request node I've named Download Image. Its method is GET. The URL points to the public web address of the snapshot we just saved. We use send header for authentication, and most importantly, under Options, Response, we set the response format to File. This is crucial. It tells the workflow, I'm downloading an image, please handle it as binary data. Great, the snapshot file is now in the workflow, but the AI can't see a binary file. It needs the image data in a language it understands. This brings us to our third node, Extract from File. This node performs one final vital conversion. In the configuration, we just set the operation to move file to base 64 string. It automatically transforms the image file into a long string of base 64 text that our AI model can process. Now for the really smart part, the AI analysis. Using a cloud AI for this 24/7 task would get expensive and it raises major privacy concerns. So we're using a much better solution, the lightweight Qwen-VL vision model running completely locally through Ollama. This keeps our data 100% private and costs nothing to run. This analysis happens in the core node of our visual branch, an HTTP request node I've named Behavior Analyze. It calls the API of our local model to determine if there's a safety risk in the image. Here, the method is post. The URL points to our local Ollama services API address. The most central part is in the body under the JSON section. Here, we build the request for our local AI. We specify the model as Qwen, and the messages contain our core instructions, the prompt, and the image data itself, which we embed using the base 64 string from the previous node. The prompt here is the brain of the operation. We've instructed the AI to act as a professional babysitter, checking for specific risks like suffocation or climbing, and most importantly, to output only a 1 for danger or a 0 for safe. This node gives us completely private, cost-free, 24/7 intelligent visual monitoring. Finally, after our local AI babysitter gives its clear 0 or 1 judgment, the logic that follows is identical to our audio branches. An if node checks if the result is 1. If it is, another HTTP request node immediately sends a notification with the alert and the snapshot to our phone. Since this judge and act pattern is the same, we've successfully closed the loop on our complete monitoring system. A 24/7 guardian that uses Frigate's ears to listen for trouble and a local AI's eyes to watch for danger, ensuring you're only alerted when it truly matters. If you want to build this yourself, I've packaged up the entire workflow and all related code. That link is in the description. The conversation continues in the comments, so tell me what automation you're curious about next. I appreciate you spending your time here. A simple like and subscribe helps this community grow immensely. Until next time, happy automating!